Hello everyone, and welcome to this introduction to dynamics. What is dynamics about? At first it sounds like it's about things that are moving. But everything moves, so is dynamics about everything? Well, almost. Let's start with this general statement. The world is made of things. Everything is a thing by definition. And those things interact. I'm a thing, my eyeglasses are a thing, this clicker is a thing, and we're all interacting. The earth is also a thing, and it's pulling me towards it. We're pulling each other, actually. So these interactions cause the things to move. And sometimes there are rules that dictate how these things move. So already, in the most abstract way to think about dynamics, you can think of objects, interaction between these objects, and how those interactions cause these objects to move. Now, in dynamics, there are ways to talk about motion and interaction. In the case of motion, we speak of kinematics. And one way to understand what kinematics means is to think of the word cinema. Cinema, kinema, have the same root, which means motion. In the case of cinema, it's pictures, motion pictures. For kinetics, it's about the interaction, and often in dynamics we speak of forces of these objects interacting with each other. And it turns out that if you take two of these objects, they're interacting with each other with certain forces, the forces are equal. This is Newton's third law. We'll see that in a bit. So sometimes there are rules. What are those rules? In the case of dynamics, we will start with the famous and most basic rule that governs all these objects and their interactions. I can describe a falling apple, the interaction between atoms, the interaction between grains of a powder, the interaction between planets and galaxies, and it can take you really far before you need other rules to describe how things work, and that's Newton's second law. Now, Newton's second law, probably you've heard of it, and probably you've seen it as F equals ma, but before we get there, actually Newton didn't write it as F equals ma. It was Euler later. So what did Newton say? Well, Newton said that the alteration of movement, or of motion, is ever proportional to the motive force impressed, and is made in the direction of the straight line in which the force is impressed. So what does that even mean? Well, first of all, alteration of motion seems to have something to do with the motion itself, right? So the change of motion, and it's proportional to the force impressed. So there's now a relationship between motion and the interaction that we just spoke about, and there is a proportionality relationship. And so that's Isaac Newton in 1687. That's the second law of Newton. All right, so what does that mean? And if we just focus on one object, one particle, here, the yellow particle we see here, well, the motion is downwards, and there are forces that are causing it to move. And I'm just going to simplify things a little further, where I just take one force. So I'm just taking this particle, pushing it or forcing it in one direction, and the motion is happening in that direction. And if I just simplify things a little bit from Newton's second law, I can say that the change of motion, or the alteration of motion, is proportional to the force impressed, or force that causes the motion to happen. So let's look at the most common kind of force that we encounter, or that keeps us together with Earth. And that's the gravitational force, the thing that's pulling us down. All right, so I have a force that's, something that's pulling us down, where if I leave this clicker go, it's going to move downwards. So how do I really describe it in this case? How do things fall? Well, before we understand anything, and let's say we're just Newton, and you want to describe things that are falling, what would you do? Right? The first step to understanding anything and that's, even before Newton, let's say Descartes or Galileo, is to quantify the thing. When you quantify something, then you can find patterns in these quantities, and then that would be your first step towards understanding things mathematically. So first, to quantify the position, we'll take a reference, which is the bottom of the screen, and we'll measure things as the height. This is just how high this particle is, and this position can be quantified in meters. So it's just a measurement stick. And let's say at a given time, you take a snapshot and it has a height r1, and then you let it fall, and it has a height r2 at the given time t2, and then let it fall even further, it gets to height r3, and then r4. Right? I'm just going to take here 4 snapshots. So if you're measuring things, you're a scientist, you're a 17th century scientist, or you're Galileo standing on the Tower of Pisa and just dropping things from up there. First, quantification becomes really important. So how do you actually measure these things? And there are 2 quantities here that we're measuring. There's, of course, the height, but what's the other quantity we're measuring that's extremely important? Here we're taking snapshots in what? In time. Right? So there's time we're measuring, and we're really, really interested here in the change of motion. So let's see if we can just measure some change of height here. So what's the change in position? It's just Ri minus Ri minus 1, or R3 minus R2 in this case. Right? So now we've introduced a few concepts: change in position, the position itself, and we've measured them. So can we actually put these things in a table? So I've just write things down. So you perform an experiment, you measure things, you measure time, and you measure the position, and just put them in a table, T and R, and you have just this table of measurements. All right, so for change, we said that you can measure change as just the difference of how things are changing. So let's say between the first snapshot and the second snapshot, it just fell by 10 centimeters, right, or 0.1 meters. But change on its own, without accounting for time, doesn't tell you much about how fast something is. And you can imagine that force has to do with how fast something is moving. So if I throw this clicker or drop this clicker with a big force, then it's going to move much faster in time. So the difference in R is not enough. I need to account for time itself. So how do I do that? I introduce this quantity, which is R2 minus R1 divided by T2 minus T1, and that's just for the first 2 snapshots. Okay? So what is this quantity? This is just the velocity. This is the average velocity of falling from the first snapshot to the second snapshot. Now the problem with this quantity is that it's defined in terms of these 2 for this interval. It's a discrete interval amount of time. If it's over 1 second or 2 seconds, of course the velocity is changing. So you can imagine breaking down this time domain into smaller bits, and so you'll have a better idea of how this velocity is changing within this interval. So can I actually measure the velocity at a given point in time? So the problem with the velocity being defined between 2 snapshots is that I cannot know what's the velocity at a given point in time, t1 or t2. I want to be able to say that at t1 the velocity is v1. So how do I actually do that? Well, one way to do it is you just take delta t to be really small. So you take the limit of delta t to be really small, and so this difference turns into what's called a derivative. And this is why Newton and Leibniz and scientists at the time started using calculus, because when you define delta that's extremely small, then you also get a continuous function that describes the change of something, not only the thing itself. Right? So we're going to call this v, which is dr dt. And now, very important, that the velocity actually has units. It's not just, the velocity is not just 3 or 4, it also has to have some physical dimension, physical meaning, and that's going to be meter per second. It's just dividing the units of r divided by the units of t. Right? And difference doesn't change what the units is. Right? If you have 5 centimeters and 10 centimeters, you subtract them, you still have a quantity in centimeters. All right, so now we can add this quantity that we've defined to the table. And now we have V1, V2, V3, something you can measure or you can just compute from the data that you have here on the left. And you can do the same thing to actually describe the change of the velocity in time. And we have the same problem if we just take delta v divided by delta t, and delta is finite, then we cannot actually define that quantity at a given point in time. So we're going to define this to be the acceleration by taking delta t to 0, and now we have dv dt, that's the derivative of the velocity with respect to time. And we're going to call this a, and now the units of a are meter per second squared. Check this for yourself. All you need to do is take the dimension or units of v, divide them by the units of t, and you'll end up with meter per second squared. And now we can also add that to the table. Now we have not only the measuring we started with just time and the position or the height, and we ended up with even more measurements that we can also use to describe what ultimately is the relationship between the force and the motion. And we said, clearly r is not the change of motion. And we said maybe it's delta r, and then we came up with the velocity. But then we said, well, maybe motion is the velocity, so change of motion is the change of the velocity, and you get acceleration. So maybe what Newton meant is the acceleration. Well, what if he really meant is just the change in acceleration? And in fact, you can keep doing that exercise of getting the derivative of the velocity, the acceleration, and higher order derivatives forever and ever. But which one is it? Right, so let's go back to this particle, and it turns out that it's just the acceleration, right? So the acceleration is proportional to the force, and what that means here in this diagram is that the gravitational force, which is pointing downwards, is proportional to the acceleration of that particle, also pointing downwards, so they have to be aligned or in the same direction. This is the second sentence in Newton's second law. So how do we write this mathematically? If I can quantify A, I can quantify F. I didn't say how I can measure F, but it's some kind of force. You can imagine intuitively what that force means. It's just pushing things or pulling something. Then it's F proportional to A. Now, what is that proportionality constant? It turns out that constant has to do with the object itself. It's a property of the object itself. And that property is its mass. So if something is heavier, then you have a bigger force exerted on it, right? And now this is tricky when you're talking about gravitation. If you've probably heard of experiments, if you take a feather and a boulder and you drop them from anywhere really, but Galileo did it from Tower of Pisa, and let's say it's in vacuum, so you don't have air, you don't have friction of air, you don't have anything pushing this particle upwards. Then they will have the same speed, they will have the same acceleration. So think a little bit about this dilemma for next time, but at least now we understand that what we're really looking at is a proportionality between acceleration and force, and that this relationship will allow us to model how things move given how they're being pushed around, that is the force. Now, the first question is what happens if you drop two things with different masses, and the second question is if you have more forces, or if the forces are not pointing downwards but you have three forces and they're pointing in very different directions, what happens, right? How can we change this expression to account for that? All right, so that's it for the introduction to dynamics, and see you next time.